Hello everyone. In this video we're going to discuss the very important concept of functions in mathematics, which we've already studied before but we'll discuss again here. And we're also going to learn how to do operations on functions, basic operations including addition, subtraction, multiplication, and division. Then we'll also look at a more complex type of scenario involving functions called composition of functions. Let's start by reviewing both relations and functions. A relation is basically any set of ordered pairs which creates an association between two sets. For example, if we look at the set involving 1, 2, 3, and 1 again, so basically the set involving the numbers 1, 2, and 3, and the set involving the letters A, B, C, and D, we could, for example, associate 1 with A, 2 with B, 3 with C, and 1 again with D. So there are no restrictions on what kind of ordered pairs you can have, whether you can repeat the same input or any other kind of restriction. As long as you have a set of ordered pairs, you have a relation. A function, on the other hand, is a relation, but with one very, very specific requirement, that no two distinct ordered pairs of this form that the function is composed of should have the same x coordinate, meaning the same first coordinate. The letters x and y aren't important. It's the notion of where they actually are located. So, for example, this relation that we saw up here would fail the function requirement because we can see that these two ordered pairs are different. When you see distinct in mathematics, basically it just means different. They're not the same ordered pair, but notice they have the same first coordinate. So this would disqualify this relation from being a function. This one, however, which associates 1 with A, 2 with B, 3 with C, and 4 with D, would be sufficient to satisfy the requirements of a function. So this would be considered a function. The set of all of the x coordinates that are involved in the definition of a function, which are also called inputs, is called the domain of the function, and the set of all the outputs, or the y coordinates or the second coordinates, is called the range of the function. Here we have two functions with finite domain and range. We usually use lowercase letters to name functions, and here we're representing it using ordered pairs as the definition dictates. But we can also represent function using this very visual and intuitive arrow diagram. And the domain here is, of course, the set of all the inputs, the first elements. So it would be the set composed of the letters A, B, and C. And the range, of course, is the set of all the outputs of the function. So we can see that would be the numbers 1, 2, and 3. We can also describe what the function does to every element, what kind of action it places on it. We know that f sends a to 1, so the way we say that is we say f of a equals 1. This notation here is not multiplication. It's a new way in which we're using this notation with the name of the function and then parentheses and then the input. So this means f sends input a to this output. F of b equals 2, f of c equals 3, etc. Now, we notice that G is somewhat different from F in that two inputs are going to the same output, and that does not violate the definition of a function. As long as each input has only one output, the definition of a function is satisfied. Notice here we can describe G using ordered pairs as A comma 1, B comma 1, and C comma 2. So notice that there are no two distinct ordered pairs which have the same first element. So that's not a problem as long as we don't have the same input going to two different outputs. That would violate two or more, of course. It doesn't just have to be two. As long as any one input has more than one output, we would violate the definition and it would not be a function. So here we can see the relation H, and it has the input A, which is being sent to two different outputs. So while it is still a relation, it is no longer considered a function. Clearly, it does describe some kind of a relationship between the set containing A, B, and C and the letters 1, 2, and 3. So it is, once again, considered a relation, but not a function. One thing to watch out for is that some standardized tests or homework assignments try to really test your understanding of functions, and they'll give you a set like this and ask you whether it is a function or not, and you may quickly take a look and say, oh, the same first element is appearing, so dismiss it as not being a function. But remember, we said if two distinct ordered pairs have the same first element, and notice these two ordered pairs, even though they have the same first element, they're not distinct because they also have the same second element. So as far as sets are concerned, repetition is moot. It doesn't have any significance. So this set is exactly mathematically considered to be the same as this set, where this set of ordered pairs that are identical is only written once. So as far as function test goes, this passes, and this relation here is also a function. Now, all the functions that we've described so far have finite domain and finite range, but most of the functions that we deal with in mathematics have infinite domain and infinite ranges. You've already seen two types: linear functions of the form f of x equals mx plus b, and quadratic functions of the form f of x equals ax squared plus bx plus c. In both of these cases, the constants are real numbers, and in this case we don't want m to be 0 because this would break this down and it would just become a constant function, and in this case we don't want a to be 0 because otherwise this would go away and we would just get a linear function. But both of those have infinite domains and ranges, as we have seen previously. Here we have a list of some of the more famous functions, and we'll also describe their domains and ranges. This is the function f of x equals x. Basically, if you replace f of x with y, you just get y equals x. And if you graph it, you'll have ordered pairs 1, 1, 2, 2, etc. And we know that if we graph that, we just get a straight line. So this is known as the 45-degree line because, of course, this angle here is 45 degrees. Now, the domain, which is the set of all the inputs or the x values that can be used in this function, would include any real number. There's no real number that would cause any kind of error here. And of course, remember, the inputs and the outputs of this function are identical. So the range, you can see, also includes all possible y values. So the range is also the set of all real numbers, which in interval notation we write -infinity, infinity. Here is one we've been looking at very recently, a quadratic function. This is the reference parabola that we compare all other parabolas to Notice the domain, once again, you can plug in any x value that you like as long as it's a real number. But the outputs, because of the squaring effect, are all going to be non-negative. So the y values associated with this graph, the y values that actually are used in the ordered pairs that create this graph, are all numbers from 0 and up. So the range actually becomes just 0 to infinity, the half open interval. Now notice that there's a bracket here because 0 is an allowable output here. So in fact, when you square 0 itself, you get 0. So 0 is part of the set of all the outputs of this function, and we call that set the range, if you recall. Here we have the cubic function, f of x equals x cubed. It looks like this. Once you graph it, you can plot some points into a table, and notice again, no problem as far as what x value you can use. So the domain is all real numbers, and here also notice the range, all the outputs will also take on all possible real numbers. So the range is also all real numbers. Here we have the square root function, which looks like this. And notice that the inputs as well as the outputs are both non-negative. So both the domain and range here become all numbers greater than or equal to 0. Of course, if you were to write them in set builder notation, they would look slightly different, because this one in set builder notation would be all x such that x is greater than or equal to 0. This one would be all y belonging to R such that y is greater than or equal to 0. So slight change in appearance if we were to write them in set builder notation. This is the absolute value function. It's very similar to this, except notice because of the effect of the absolute value, this part has jumped up and become positive as well. So notice that the domain is all real numbers. Every real number is contributing to this graph. And the range, though, like the quadratic function, is only non-negative numbers. So the range is going to be all y such that y is greater than or equal to 0. Here's a function we'll get to study very soon. It's called the exponential function. And this is a graph that is used to describe processes that grow very quickly. So you may have heard of the word exponential growth. This graph right here is precisely demonstrating that kind of growth. Of course, with all these graphs, we haven't put arrows at the ends, but remember, all of these go on ad infinitum. They don't stop just where you see them stop in the graph, okay? So this one also has an interesting quality, because notice it's approaching the x-axis. Now, it's hard with technology to try to show the reality of this situation, but this actually never touches the x-axis. And because of that, we call the x-axis in this graph a horizontal asymptote of this graph. And an asymptote is basically a line or a curve that another curve gets arbitrarily close to, which means as close as you want to get it, but never actually touches. And notice here, there's a subtle difference in these ranges, in that this one does not include 0. We have a parenthesis here, because remember, this never actually takes on the y value 0. Also of interest to us is the fact that every single one of these is a function, because it passes a test we've discussed previously called the vertical line test. What that says basically is that if no vertical line crosses the graph of a given relation, and remember, they're all relations as well, then that relation is a function. And notice there is, for every single one of these graphs that you see, you cannot find any vertical line that would cross these graphs more than once. So they all pass the vertical line test for functions. Here we want to take a look at why it is that relations such as this one depicted here that clearly fails the vertical line test. Notice there, this vertical line, for example, crosses it more than once. This relation is described by this equation, x equals y squared. And we notice that if we take the x value 4, there are two y values that we can square to get at x value, namely 2 and -2. So this creates the exact situation that functions need to avoid. We have distinct ordered pairs which have the same first coordinate. And of course, this means that these kinds of graphs fail the necessity of being a function, the required condition that no two ordered pairs that are different have the same first coordinate. And of course, that means this relation sends the input 4 to two different outputs, 2 and -2. So this line clearly indicates this violation that is occurring as far as the relation trying to pass the test of being a function. So of course, there's no need for there just to be 2 points. This could be some kind of a spiral, in which case this line may have intercepted it countless times or infinitely many times. But as long as there's 2 or more, we have enough to realize that we're not looking at a function. All right, so we have previously studied the 4 basic operations of addition, subtraction, multiplication, and division on mathematical expressions. As it turns out, a function is also a special kind of mathematical expression once defined, and we can perform the same operations on functions as well. So the definitions are quite straightforward and simple, and here's the visualization. Like here we have a function f and a function g, and when we add them we get this other new function which we call the sum function. So that itself is also a function. As far as the domain of the sum function or any of these other functions is concerned, we basically need to just take the intersection of the 2 domains. So basically, the output of f added to the output of g at any given point will give you the output of f plus g at that point. And you can see that here visually. When it comes to addition and subtraction, you can kind of visualize it pretty easily. Like here you have a function f and a function g. When you subtract it, you get this lower function f minus g. Once we get to multiplication and division, the relationships become quite complex, not easy to guess or visualize. So here we have the sum function, the difference function, the product function, and the quotient function. Remember, we discussed about the fact that the domain of each of them is the intersection. The only exception is f over g, where we need one extra requirement, and that is, of course, the fact that g of x should not be 0, because otherwise the quotient here becomes undefined. So that's the extra requirement for only the quotient function. So basically f plus g of x, the value or the definition of f plus g of x is just going to be whatever f gives us at that point. Let's say x is here, plus whatever g gives us at that point. So the output of f plus the output of g. For f minus g of x, it's going to be the output of f of x, minus the output of g at x. For the product function, same way, and also for the quotient function. So here we have a couple of functions defined for us. F of x equals x squared plus 1, and g of x equals 5x minus 3. We have a quadratic function here and a linear function here. We want to perform these basic operations on those two functions. So basically, we know from the definition that f plus g of x is just going to be f of x plus g of x. So we know what f of x is. It's x squared plus 1. And we know g of x is 5x minus 3. And because we're adding, we don't really require parentheses around the 5x minus 3. If we were doing any other operation, we would put it, as you'll see in a minute. So now it's just a matter of, simplifying this expression. And we know that the only like terms are the 1 and -3. So we end up with x squared plus 5x minus 2. And this is basically what is meant by f plus g of x. Now for f minus g of x, it's going to be very similar. So we're going to get f of x minus g of x. So f of x is x squared plus 1 minus, this time we do need parentheses because g of x has more than one term and this negative needs to be distributed by them. So we write minus quantity 5x minus 3. Now we're going to just distribute and simplify. So x squared plus 1 minus 5x plus 3. So we end up with x squared minus 5x plus 4. And that is what f minus g of x is going to be. So we can just say f minus g of x equals x squared minus 5x plus 4. Now for f times g of x, by definition we know that f times g of x is going to be f of x times g of x. Now we know that f of x is x squared plus 1 and g of x is 5x minus 3. So we parenthesize both of those, and now we just go ahead and multiply them in the same way that we learned when we covered polynomials. So we'll go ahead and distribute the x squared into this group, and when we're finished we'll go ahead and distribute the 1, then we'll combine any like terms. So we get 5x cubed minus 3x squared. Now we're going to distribute the 1, so plus 5x, and then positive 1 times negative 3 gives us minus 3. So now we see if we have any like terms, and we notice that we do not. So we're basically finished. So as far as what f times g of x is concerned, we just have 5x cubed minus 3x squared plus 5x minus 3. For f over g of x, we also apply the definition. When we want f over g of x, we need to calculate basically the output of f and divide it by the output of g at that input x. So we know that f of x is x squared plus 1, and g of x is 5x minus 3. So that is basically f over g of x. Now, with this one in particular, we do want to make sure that we avoid 5x minus 3 being 0, which means x equals 3/5. So when we want to write the domain for each of these, notice that these are two polynomials, and we know they're very well-behaved functions with domains being all real numbers. So when you take the intersection of all real numbers with itself, that's just going to be all real numbers. For basically all three of the first ones, the domain is just going to be negative infinity to infinity. The only exception being the last one, we need to make sure that we exclude 3/5 from the domain of f over g. So basically the way we handle that is we'll say negative infinity all the way to 3/5. We're going to exclude that, so we'll use parentheses. Union, we can have everything after 3/5 as well. So 3/5 comma infinity. So that's how we compute the domain for those. Now, when it comes to f plus g of 2, for instance, here we're evaluating these specific outputs like f plus g of 2, and we notice that we could do it two ways. Since we've already calculated f plus g of x, we could go ahead and just use that and plug in the 2 into this expression to give us f plus g of 2. So that would give us f plus g of 2 equals 2 squared plus 5 times 2 minus 2. So that's going to give us 4 plus 10 minus 2, and we know that that's 12. And that is f plus g of 2. Now, just so that you get more depth into this situation, notice that we could have also done it without using this. In other words, let's suppose there was a problem that didn't need you to find f plus g of x, and they only asked you for f plus g of 2. If that were the case, you wouldn't have to go sit there and calculate f plus g of x so that you can then plug in 2. You could have just done it directly. By definition, notice that f plus g of 2 is going to be f of 2 plus g of 2. So we know that f of 2, remember, that means wherever you see x in the definition of f, substitute 2. So that would be 2 squared plus 1. And g of 2, wherever we see x in the definition of g, we're going to substitute 2. So we get plus 5 times 2 minus 3. So we end up with 4 plus 1 plus 10 minus 3. So that's 5, 15, 12. Not surprisingly, we get the same result. So just remember, two different ways of handling the same evaluation. Like that. So again, you could use the result you obtained for f plus g of x here. Let's make it look better.
I'm not sure.
Or we could do it directly. All right. So now we're going to handle f minus g of 2. Again, we have already calculated f minus g of x. So we could go ahead and use this fact to calculate f minus g of 2 for the specific input 2. So we would get f minus g of 2 equals, wherever we see x in this expression, we're going to substitute 2. So we get 2 squared minus 5 times 2 plus 4, which gives us 4 minus 10 plus 4. So that's basically 8 minus 10, which is negative 2. And that is f minus g of 2. Notice that we could have also done it directly again by just computing, by realizing that f minus g of 2 by definition is f of 2 minus g of 2. We could have bypassed having to use this altogether, and then we could have just gone directly to the definitions of f and g. So f of 2, that means 2 squared plus 1, minus, let's not forget the parentheses, g of 2, which is going to be 5 times 2 minus 3. So we end up with 4 plus 1 minus, that's 10 minus 3, which is 7. So that's 5 minus 7, which is, again, not surprisingly, negative 2. So we end up with, once again, f minus g of 2 equals negative 2, in agreement with our indirect approach by first computing f minus g of x and then evaluating for the specific input 2. And of course, this goes on with f times g as well. So we know that we can use this result, which we've already obtained, for f times g of x. So we can say f times g of 2 equals, wherever we see x in this expression, we're going to substitute 2. So we get 5 times 2 cubed minus 3 times 2 squared plus 5 times 2 minus 3. So we're going to get 5 times 8, which is 40, minus 3 times 4, which is 12, plus 5 times 2, which is 10, minus 3, and that gives us negative 12 plus 10 is negative 2, minus 3 is negative 5, so 40 minus 5 is 35. So that's f times g evaluated at the input. I mean f times g evaluated at input 2. And let's do it directly now. So to do it directly, we don't use the result we obtained here. We don't rely on it. We just go directly to f of 2 times g of 2. And notice f of 2, we've calculated a few times already. That's 2 squared plus 1 times g of 2, which is going to be 5 times 2 minus 3. So that's 5, and that's 10 minus 3, 7. So we get 5 times 7, which is, of course, 35. So whether we calculate it directly by going just straight to f and g definitions, or indirectly by first computing the product function for a general input x and then just substituting the specific input 2, we get the same result. The last one is f over g of 2, and of course 2 is not a problematic number. It is in the domain of f over g because it's not 3/5, so we can go ahead and compute it safely. So f over g of 2. Now notice that in this case, whether you do it using this or go directly, it's going to be pretty much the same thing. So here we're only going to calculate this once, and we're going to get 2 squared plus 1 over 5 times 2 minus 3. So we get 5 over 7, and that is f over g of 2. So you can see these operations are very straightforward, very simple, but important. You'll be encountering them all the time as you proceed with mathematics. So just make sure you have these down and then we'll proceed. Now we want to look at a slightly more interesting kind of operation we can do with functions, and that's called composition of functions. Basically, sometimes it's necessary to use the output of one function as the input for another function. This kind of sequential functional operation and the process involved is called an iterative process. It's a very important kind of process which is used in various fields. Now, just to give you a quick example for where this can become handy and how powerful it is, suppose that you go to your favorite clothing store and there's a major promotional event. So basically, your favorite jacket that you've located on a rack is $100, and above that rack it says 30% off of every item on this rack, right? Now, as you were walking into the door, you also noticed that it said an additional 20% of already reduced prices at the register at the time of checkout, right? So how much do you think you'll end up paying for your favorite jacket, which was originally marked $100? So you may be surprised to find that most people would miss that question, because the way most people do this in their heads is the following. They go, okay, oh, 30% off here, another 20%, so that's 50%. 50% of 100, I should be paying $50 for this jacket. That's awesome. Let's go purchase it. And of course, they're going to be a little upset at the register when they find out that it doesn't actually come out to be 50. It ends up being more than 50. And here is the mistake that was made when you did that addition of the 20% and the 30%. Because remember, what the cash register is programmed to do is the following. The cash register is programmed to take 30% off of the 100 and then take another 20% off of that. So here we're missing a parenthesis. Let me add that. So the correct way of actually calculating this event would be, you start with your $100, you take 30% off of that, which is 30% of that $100, the original $100, and you get 100 minus 30, which is 70. Now we have a new number that we need to reduce by 20%. So now we have to take the 70, take away 20% of, you guessed it, 70, not the original 100. And we end up with 70, 20% of 70, that's just 0.2 times 70, so it's 14. So you get 70 minus 14, which is what? More than you thought, isn't it? 56. So be very careful when you get this kind of an offer. Of course, most retailers want you to have that, sense. Not all. I'm sure there are some honest retailers out there, but most of them want you to think you're getting 50% off. And let's face it, most people, they don't think twice about, what they're actually going to pay at the register. And the fact of the matter is, I used a very simple example here. Usually the numbers aren't that simple and so quick to calculate. So I don't blame you if you haven't looked into this that deeply on a busy shopping day. So let's see how composition of functions can be handy here. So here's how we could have done this problem using two functions and then the composition of those two functions. So notice that we can create one function called price after a 30% discount. Of course, we'll set that up as f of x equals 70% of x, because remember, we want this number here to be what you're actually going to pay, not just the discount. If we just wanted to compute the discount, we could have used 30% of x. But if to make it easy, we'll just calculate what you're actually going to pay. So f of x equals 70% of x will tell you how much a price of an item is once it's been discounted 30%. Then we'll create another function, g of x, which is basically, you can call it the price after a 20% discount function. So that one will be, of course, g of x equals 80% of x. Now, which is of course just 0.8x for simplicity. This is the function that is being handled after this function has been already taken care of. So we could get the answer 56 that we found after several calculations with just one nice calculation. And here's what we do. We're going to first basically compute f of 100, which is, remember, we're going to plug in 100 into the 30% discount function, which is 0.7x. And then once we've done that, once we've computed that, we're going to apply the g function to that. So this is what we mean by composition of functions. The output of the function f is becoming the input of the function g. This is what we meant when we said the output of one function becomes the input of another. So notice this just means g of, what is f of 100? f of 100, you're going to plug in 100 here. So you get 0.7 times 100. That's where this comes from. And of course, 0.7 times 100 is just 70. So you're now going to compute the g function, the 20% discount function, for that number, which was the output of the original function f. And of course, what is g of 70? That's just going to be 0.8 times whatever this x is, which is now 70. And this way you get 56. So this is really the fastest way to compute something like this if you care to actually take the time to do it. So this kind of functional evaluation where the output of one function becomes the input of another function is called the composition of the two functions. And we formally define it in this way. We say let f and g be two functions. The composition of f and g, called the composite function, is given by this. First of all, we use this notation. This is not a multiplication notation, so be very careful. It's kind of like an open circle. Sometimes people say f circle g of x. What is that? That is f of g of x. In other words, you start with x, you compute g of x, the first function, then you apply f. Now here we had to do it in a different order, but here if I say the composition of f and g, that means you're going to start with the function f. If I had said the composition of g and f, you would have written g circle f of x. So the order is important, especially because we're going to find out soon that this operation is not commutative. What that means is f circle g does not always equal to g circle f. Remember, when we say a certain operation is not commutative, we don't mean it always fails. We mean there is at least one case in which it fails. The standard of truth in mathematics is extremely high, so even if a given fact fails once, we don't allow it as an actual fact anymore. So given that for some pairs of functions f and g, f circle g does not equal to g circle f, that's enough for us to say that composition of functions is not a commutative operation. Now the domain of f circle g is going to be a little bit more complex than we're normally used to, but it'll make sense if you think about it for a minute, because it says it's all x in the domain of g. Why? Because we have to calculate g of x first, right? Such that g of x itself is in the domain of f, because otherwise, if this were not in the domain of f, we wouldn't be able to compute f of g of x. So do think about this for a minute, make sure it makes sense to you before we proceed. And once again, remember that generally speaking, composition of functions is not commutative, but we will find some instances where it is always going to commute. All right, so here we have two functions, and we're going to find both f circle g of x as well as g circle f of x. Then we'll also compute the composition for specific values, such as in this case 1. So let's go ahead and begin. So remember that f circle g of x by definition means f of g of x. So that means f of, now what is g of x? In this case, 2x minus 5. So f of 2x minus 5. So what that means is, you see this expression for f of x equals x squared plus 3x plus 2. You have to understand this in a very general sense. What this says is that whatever you feed this function f, think of it as a machine, right? These are the things it'll do to it. It'll square it first, then it'll add that to 3 times itself, and then it'll add 2. So whatever you feed, so for example, if I were to feed this function f, say a delta or a triangle, it would do the same thing. It would take that and square it, and then it would add 3 times itself to it, and then it would add 2. So now, instead of this delta, imagine you're going to feed it this, 2x minus 5. So what is it going to do? The same thing. It's going to take the 2x minus 5, and every place you see x, it's going to put 2x minus 5 instead. So it's going to square the 2x minus 5, then it's going to add that to 3 times that 2x minus 5, and then it's going to add 2. So it's going to go 2x minus 5 squared plus 3 times 2x minus 5, and finally plus 2. So remember, every place you see x, since you want f of 2x minus 5 instead, replace the x with 2x minus 5. Every instance of x. So here x became 2x minus 5. For 3x, the x became 2x minus 5, and the 2 doesn't change because there's no x in it. So now we're going to square 2x minus 5. We know that becomes 4x squared minus, remember, 2 times the first times the last, so 4x times 5 is 20x plus 25, and then plus, now we're going to distribute the 3 here, so we get plus 6x plus minus 15 plus 2. So basically we have let's double check, 4x squared minus 2fl, so 4 times 5 is 20x plus 25 plus 6x minus 15 plus 2. So now we notice that we have some like terms. We notice we have like terms here. Let's see, this is not letting me change colors for some reason. All right, so we notice we have these like terms, and we also have 25, negative 15, and 2, which are like terms, which we're going to combine now. So we end up with 4x squared minus 14x, 25 minus 15 is 10, 10 plus 2 is 12, so plus 12. And that's basically f circle g, or f compose g of x. So we have 4x squared minus 14x plus 12. You always want to represent your answers in a professional, coherent manner. All right, now we want f circle g of 1, right? So again, we have options. We could use this result, which we already obtained for f circle g of x, and just go ahead and compute it for this particular input. So we're going to plug in 1 wherever we see x in this expression. So we end up with f circle g of 1 equals 4 times 1 squared minus 14 times 1 plus 12, which is, of course, that's just 4 minus 14 plus 12. 4 minus 14 is negative 10, plus 2 will give us positive 2. All right, so that's using f circle g of x result. But what if the problem didn't care for you to find this and they only wanted you to compute that? Do you need to go through all this and then get the 2? No, you don't, right? You could have just gone directly to what f circle g of 1 means. So we're done with it. We're just doing it in an alternative way now. So notice that just means f of g of 1 by definition. So that means f of, let's go to g now and see what g of 1 is going to be. Remember, you're going to plug in 1, so 2 times 1 minus 5. So that's going to be 2 times 1 minus 5. That's just, remember, that's just g of 1, okay? So basically you get f of, that's 2 minus 5, so it's negative 3. So now it's time to go to f and compute it for input negative 3. So wherever we see x in this definition, we're going to put negative 3. So we get negative 3 squared plus 3 times negative 3 plus 2. Now that's 9 minus 9 plus 2, which of course gives us 2 as we obtained here. So no matter how we go about it, we realize that f circle g of 1 is going to be 2. All right, which is of course the same thing we found here for f circle g of 1. All right, so now we're going to turn it around, and this time we're going to compute g circle f of a general input x. So g circle f, you should definitely try this on your own before you join me back at the video. Go ahead and hit pause and do this. You should be able to do this now. So that's g of f of x, assuming you're back now. So that's g of, now remember, we need to know what f of x is, and we know what it is. It's x squared plus 3x plus 2. So now we need to go and apply the action of g to this input, x squared plus 3x plus 2. What is the action of g? What does g do to an input? G doubles the input and then subtracts 5, right? So what is g going to do to this input? The exact same thing. It's going to double it and then subtract 5. So remember, wherever we see x in this definition, we're going to replace x, we're going to take it, and instead of it, we're going to put that. So we're going to get 2 times x squared plus 3x plus 2. Don't forget the minus 5 that comes after. So we end up with 2x squared plus 6x plus 4 minus 5. Now if we simplify and combine, we end up with 2x squared plus 6x minus 1. And that right there is G circle f of x. Now, one of the things we were asked is to see if they're the same. Notice f circle g of x was 4x squared minus 14x plus 12. G circle f of x equals 2x squared plus 6x minus 1. Clearly, in this case, f circle g of x does not equal to g circle f of x. Remember, this one example is all we need to firmly say that composition of functions is not a commutative operation. This we call suppose somebody comes to you and says, hey, did you know the composition of functions are commutative? You can say, no, I have a counter example. This would be what we call a counter example in mathematics. And all you have to do is show them this one example and say, see, no, you were mistaken, friend. They're not. It is not. A composition of functions is not a commutative operation. All right. So now we're going to compute G circle f of 1. And I encourage you to pause and calculate it in both the ways that we have been discussing. Indirectly, by using this, or directly by just using g and f themselves. So here we're going to, in this expression, wherever we see x, we're going to put 1. So we get 2 times 1 squared plus 6 times 1 minus 1. So we get 2 times 1, which is just 2, plus 6 minus 1, which is 8 minus 1, which is 7. So that is G circle f of 1. Now we'll do it directly without using this, assuming that some problems may never ask us to find the G circle f for a general input x. They might just want this specific value of G circle f, right, for some application. So we should not have to go through all that. We can just say G circle f of 1 equals G of f of 1. Remember, both of these are not required. I'm just getting a point across here, right? Otherwise, you just need to use one of the methods. All right, so we get G of, okay, now we need to go find out what f of 1 is. Remember, here's f of x up here. So wherever we see x, we're going to replace it with 1. So we get 1 squared plus 3 times 1 plus 2. So that's basically G of 1 plus 3, which is 4, plus 2, which is 6. And now, here's the function g. We're going to use 6 as the input. So wherever we see x in this expression, we're going to replace it with 6. So we get 2 times 6 minus 5, which is 12 minus 5, which is 7. Not surprisingly, we already knew that. We were just making sure that we did it correctly. This is a nice way of checking to make sure that you've done everything correctly, because if these two don't match, there's something wrong, right? We need to go figure out where we made some kind of an error. All right, so make sure you can handle these. These are not difficult, as you can see, but a lot of students run into problems with these because they have a hard time not treating this as multiplication. Remember, this is not multiplication. This is composition, and in order to do them, you have to understand the basic definition that f circle g of x means f of g of x, and g circle f of x means g of f of x. All right, so let's go ahead and do one more problem and we'll call it the day. How's that? Okay, here's our last problem for this video, and we're given two functions. One is the cube root of x minus 5, the other one is x cubed plus 5. We're going to go ahead and calculate both f circle g as well as g circle f, and then we'll go ahead and compute it for a particular number as well. All right, so let's see what f circle g of x is going to end up being. So we have f circle g of x. We know that's going to be f of g of x. I do hope that you tried it on your own first before you rejoined me. All right, so that means f of what? Well, g of x. What is g of x? It's x cubed plus 5. So that means f of x cubed plus 5. Now, we need to apply the action of f to a general input to this input now. So what does f do to x? It takes the cube root of whatever that x is and subtracts 5. So what is f going to do instead to this expression? The same thing. Wherever you see x over here, you're going to replace that with what? With this expression. So that's going to be the cube root of, instead of x, we're going to put x cubed plus 5. And then subtract 5. So notice that becomes the cube root of, the 5's are going to cancel out, so you just get the cube root of x cubed. Well, isn't that nice? Because we know what the cube root of x cubed is. Remember our rule? The nth root of x to the n, particularly when n is odd, is definitely going to be x. Sometimes when it's even and the x values can take on negative results, we have to put absolute value of x, but here n is odd, so we can safely say it's x. All right, so that's f circle g of x. Now, so what is f circle g of 1 going to be? Well, here is f circle g of x. So f circle g of any number is itself. So what is f circle g of 1 going to be? Well, it's going to be itself, which is what? 1. So this is particularly a simple one. But I wanted to deal with it because as soon as some people say cube roots, etc., they panic. So I just wanted to show you how simple some of these can be. All right, g circle f of x. So we know that by definition. Okay, before we do that, let's stick to tradition. Let's go ahead and figure out f circle g of 1 without relying on this result. Let's do it directly. So that means f of g of 1, right? So that means f of what? Well, we got to figure out what g of 1 is. Remember, g of x is x cubed plus 5. So what is g of 1? Well, instead of x, put 1. So it's going to be 1 cubed plus 5. So we get g of 1 cubed plus 5. F of 1 cubed plus 5. And we know 1 cubed is 1 plus 5 is 6. So we get f of 6. So now we have to go to the definition of f, and instead of x, replace it with 6. So f of 6 is just going to be the cube root of 6 minus 5, which is the cube root of 1, which is 1, as we expected. And that is f circle g of 1. All right, so now let's look at g circle f of x. So g circle f of x, that's the composition of g and f, so that's going to be g of f of x. So it's going to be g of, remember, we need to put what f of x is here. So f of x is the cube root of x minus 5. So it's going to be g of the cube root of x minus 5. So now we need to apply the action of g to this new input. So whatever g does to an input, we need to do to this input. What does g do? Well, look, it cubes and adds 5. That's how you have to look at it. What does g do to whatever you feed it? It takes what we feed it, cubes it, and adds 5. What are we feeding g now? We're feeding it cube root of x minus 5. So what is it going to do? Where you see x, replace it with this. So it's going to take the cube root of x minus 5. It's going to cube it, and then it's going to add 5. And notice the cube root of some number, so that's a relative of this rule, which said if you have the nth root of x and then raise it to the power of n, you also just get x. So here the cube root of x minus 5 cubed is just going to be x minus 5. And then we're going to add 5, so we end up with x. And that is g circle f of x, right? And listen to the question they had. Are f circle g and g circle f the same for these functions? Well, they definitely appear to be the same. So here, f circle g of x does equal g circle f of x. So you may be confused. You say, hey, you just told us it's not commutative. It's not always, yeah, but if you recall, I said even if it fails in one instance, you can go ahead and say it's not a commutative operation. So does that mean it never works out? Yes, for certain functions it does work out. And for this particular class of functions, and I'm discussing it here because this is going to be what we're going to cover in the next video. These are a very special pair of functions called inverse functions. For inverse functions, this will always be the case. They basically cancel each other effects out, and you always get the input that you started with. So this is not surprising, and you will understand it much better next time, but this time I just wanted to take a quick look at it. All right, so let's go ahead and compute g circle f of 1 to wrap things up. So g circle f of 1, well, if we use this result, which says g circle f of any input is itself, that's going to be quick. That's just going to be 1. Or if we do it indirectly, or actually directly, this was indirect because we found it by using this result first. So we're going to do it directly now by realizing g circle f of 1 means g of f of 1, which is g of, we need to compute f of 1. Notice that's going to be the cube root of 1 minus 5. So we get the cube root of 1 minus 5. So now we need to apply the action of g to this outcome. But let's go ahead and simplify that a little bit more. So that's g of the cube root of -4. So what does g do to an input? G takes the input, look, in this case x, it cubes it and then adds 5. So whatever you feed this machine g will cube it and then add 5. So what are we feeding it now? We're feeding it cube root of -4. So what is it going to do to that? It's going to cube it, right? And then add 5. Now, what is the cube root of -4 cubed? Well, remember, the cube root of any number to the power of 3 is just going to be the number. So that's just going to be -4 plus 5, which is going to be 1, as we found already indirectly. So here we have g circle f of 1 equals 1. All right, so that's basically operations on functions, and then a more complex type of operation called composition of functions, where the output of one function becomes the input of another function. All right, so make sure you master these before you watch the next video, because we're going to require these skills. The next video is going to be titled one-to-one functions and inverse functions. We're going to talk about one-to-one functions, and they are a class of functions that always have a function associated with them called the inverse function, and that's what's coming next. So be safe until our next meeting.